Hello and welcome back. Today we're going to be talking about some fun chemistry. Now, this actually bridges the gap between chemistry and physics because it's nuclear chemistry. All those electrons that we're used to when we're talking about chemistry, those things that are farthest off, it's the first thing that another molecule or atom's coming in interaction with when it comes to us, we're going to completely ignore those. And we're only going to focus what's going on in that little tiny nucleus right in the middle. And that is our nuclear chemistry. We're going to talk about the types of radioactivity, kind of the basic ways that molecules change their identity. And then we're going to talk about some of the trends that we see, what's called the valley of stability, and how we can predict, oh, this molecule, or sorry, this atom might undergo radioactive decay in this way because it wants to increase its neutrons or decrease its neutrons. We're going to talk about a little bit about detection of radioactivity, the kinetics of it, how fast it is. And we're going to talk about the energetic equivalence. We're going to talk about E equals mc squared. I mean, that equation you've always heard. We're actually going to use it, okay? And fission and fusion. How do we actually use this kind of energy to do something? And then a little bit about radiation and medical applications and radiation in your daily life. Like, hey, look around. I'm going to ask you a question. How often do you think you're exposed to nuclear radiation? Like, I really mean like products from nuclear radioactive decay. Like, there's actual like radioactive material, and the stuff from that radioactive material is hitting you. Okay, that's what I'm asking. And that's very different from different forms of light. Like, people worry about the radiation from their phone. No, that's not radiation that I'm talking about. That's light. Okay, it's light in the radio frequencies. I'm not worried about that. I'm worried about actual things that are coming from nuclear radioactive decay. How much is hitting you? And I want you to make an estimate. Just like pause the video, write something down. Like, I think it's, I gave you a couple examples, 500 counts of radiation every minute. I think it's 10 counts of radiation every year. Whatever it is, big number, small number, how much do you think you're getting? And then towards the end of our set of videos, not towards the end of this first video for those just watching on YouTube and not doing the whole class, for the end of this set of videos on nuclear chemistry, we're going to talk about how much you're actually hit by and where all that radiation is coming from. All right, so just a reminder on nomenclature. When you have something like carbon, what do? At the bottom left, you write the atomic number, right? Which we generally consider to be the number of protons. Okay. Now, we're going to extend that definition a little bit in nuclear chemistry because we're occasionally going to draw things like electrons. And right, it's got no protons, so you might think, oh, let me put a 0 down there. But that's not what we do. It turns out we're going to put a -1 down there. And so what I'm going to say, instead of the atomic number or the number of protons, it's kind of like the core charge. Right? For a carbon atom, the core charge is the charge in the nucleus. For just an electron, the core charge is, well, I'm just an electron, that's all I have. And so my core charge is -1. Okay? On the top, you get the mass number. One of the most unfortunately named things in chemistry, because it's not the actual mass, it's the mass number. It's just the number of protons plus the number of neutrons. And we're actually going to maintain that one entirely. It's just a count of the number of protons and the number of neutrons. And if you just have an electron, it's 0, right? Because there's no protons and no neutrons in an electron. So we put those things. If we had a charge, we'd sometimes put it up here. So if we had C+, right, we put it over there. Here, you can put a minus there for the electrons. So we're going to continue to use that notation as we do our nuclear chemistry and balance nuclear reactions. All right, so let's go straight into it. Let's say an atom is sitting there and decides, I'm not happy. I want to be different. And so how can it be different? And we'll talk about the why it wants to be different in just a little while. But let's talk about the how it's different first. So an atom sitting there says, what can I do to be different? And it turns out it's got a bunch of different paths available to it, some of which are going to be more energetically favorable than others, depending on the status of that particular atom. But remember, radioactivity is always a function of atoms, never a function of molecules or things like that. It's just one little atom sitting there trying to decide whether or not it wants to decay. Now, we can't predict. We can't just look at an atom and say, oh yeah, you're going to decay right now. No, it doesn't work that way. It's a statistical process. It's just like if you're popping popcorn in the microwave. You couldn't look at a single kernel of popcorn and absolutely for certain predict that that kernel of popcorn is going to pop at 1 minute and 37 seconds. But you can say, you know, I think there's like a 90% chance that that particular popcorn kernel is going to pop within 2 minutes of me putting the popcorn in the microwave. That you can say. So it's a statistical thing. But when it does decide to do it, it does it. So we're going to talk about the different ways. The first way is what's called an alpha particle. And so we're going to take some uranium. Uranium is very common in the world and is also very radioactive. And uranium has an atomic number of 92. And we're going to talk specifically about an isotope of uranium called uranium-238. Remember, isotopes have the same atomic number, but different mass numbers, so different numbers of neutrons. So you can have uranium-238, you can have uranium-236, or whatever, and it just changes the number of neutrons. And that can decay via an alpha particle. Now, what is an alpha particle and what does it mean to decay? It means that little nucleus is sitting there with all its little nuclear particles. Right? And some of those are protons, some of those are neutrons. And all of a sudden, for no particularly good reason that we can figure out, right, it decides, hey, I'm going to eject things from my nucleus. So we're not talking about losing electrons, we're talking about the nucleus actually changing and breaking apart. And in this case, what it's going to eject is 4,2 He. So it's actually going to eject a helium nucleus from itself. Now, notice I wrote that helium nucleus on the product side. I put the arrow first. It's a product. So nuclear radioactive decay is not a reaction with something. It's just this one thing spontaneously goes and decomposes into more than one thing. And in this case, it's going to decompose into the helium. And, you know, in case you're wondering, yes, most helium in the world comes from nuclear radioactive decay. So when you get your little balloons for your party, you say, look, nuclear radioactive decay particles, because that's actually where they came from. Yeah, I know, it's nerdy, but cool at the same time. All right, so what's left, right? After it ejects this, what particles are left here? I mean, uranium was a big one. It lost a couple things. Well, it turns out in order to figure that out, we have to balance a nuclear reaction. And how you balance a nuclear reaction is really, really easy. You balance the mass number and you balance the atomic number. That's all you do. So if we balance the mass number up here, all we do is use this arrow as an equal sign. We say 238 is equal to 4 plus x. And down here we balance the atomic number. 92 is equal to 2 plus y. And we figure out what x and y are. And it doesn't take long to figure out that 238 minus 4 is 234, and 92 minus 2 is 90. Then we have to run over to a little periodic table, and we say, hey, periodic table, what is element 90? We find element 90 there, and it's the good old god of thunder, which is thorium. Okay, so how we can say this out loud is say, oh, uranium-238. Remember, that's how we talk about isotopes. We just say the name and the mass number. We don't say the atomic number. Uranium-238 undergoes alpha decay in order to form thorium-234. Now, alpha, right, that's different because I didn't write alpha here anyway. And if you remember your Greek alphabet, an alpha looks something like that. Or, you know, people who are fancy like make these like little, I don't know. I just draw an alpha like kind of like a fish. And so alpha looks like that. And it turns out that we can write this 4,2 He as 4,2 He. We can write it as alpha, and we can write it as 4,2 alpha. And all three of those ways of writing it are entirely equivalent. So you have to be familiar with all of them in order to interpret nuclear radioactive decay processes, and you have to be able to use them in order to actually write your own nuclear radioactive decay process. So up here, instead of my 4,2 He, I could erase that, and I could just write alpha. Right? The mass number and atomic number aren't shown there, but we have to know that, oh, alpha has a mass number of 4 and an atomic number of 2 in order to do our balancing. So that's one way that something just sitting there can spontaneously fall apart. What's another way? Another way, if you remember alpha, the next character is beta. And what is a beta particle? So beta, if you remember, it's like a bee with a tail. In fact, it's like got this little thing here, but I rarely draw that. I usually just, you know, make my bee with my big tail on it. And then what's a beta particle? And a beta particle is an electron emitted from the nucleus. And you're like, oh, that's interesting. An electron emitted from, wait. How many electrons are in the nucleus? You're like, none. There's no electrons in the nucleus. I can even find videos of you telling people that in the nucleus there are protons and there are neutrons and the electrons, right? The nucleus is this little tiny thing. The electrons are really far away. Where's the electrons in the nucleus? How can I emit an electron from a nucleus and you tell me that that's okay? Well, let's do an example first, and then I'll tell you where it comes from. So if you are doing carbon-14, we're going to put a 6 down there. Remember, you don't always have to put the atomic number. You can just write carbon-14 like that. You do have to write the mass number if you're talking about isotopes. And that's going to undergo beta decay. And what's it going to form? Well, beta is an electron. If you remember from that slide a few slides ago, I said, hey, we can write that as -1 and 0. -1 being the fundamental charge, 0 being the number of protons plus neutrons. And so we get 14 is equal to 0 plus 14. 6 is equal to -1 plus, and people always get this one messed up, so let me write that out. 6 is equal to -1 plus x. You add 1 to both sides, you get x is 7, right? Not 6, not 5, but 7. All right, and then you look up element 7 on the periodic table, and that's nitrogen. So carbon-14 undergoes beta decay in order to form nitrogen-14. And this, folks, is alchemy. I mean, this is what the alchemists were looking for. We're changing one element into another element. The only difference between us and the alchemists is we're not doing it because we can. We're just watching nature do it. The alchemists thought that, hey, if we did things right, we could do this on purpose. And you can't really do that. You can nudge nature along to what she might already do, but you can't actually make radioactivity happen without doing some pretty crazy stuff. All right, so where is this electron coming from in the nucleus? I mean, we're going from 6 protons to 7 protons. I mean, we're creating a proton. How can we create a proton? And it turns out that here's the crazy thing. When you have a neutron in your nucleus, it turns out that a neutron isn't just a neutron. A neutron is a proton and an electron squished together. Remember, the proton is positively charged, the electron is negatively charged. So when you squish those two things together, they actually cancel out each other's charge, and you get this thing called a neutron. And they're so strongly attached that it's like they're one thing, even though they're actually made up of 2 things. Crazy. So here we go. We've got this neutron. It's a proton plus an electron. And one of them, just randomly, who knows which one, why that one, why not another one, one of them in there decides, hey, I'm giving away my electron. I'm turning it into a proton. And it does it. And it does it all the time. Carbon-14 does it all the time. And so then we're left with an additional proton where we used to have a neutron. So a neutron and proton, those both count into the mass number. So mass number didn't change, but atomic number went up by 1 because a neutron changed into a proton. I love this stuff. It's so counterintuitive, but that's what happens. All right, if you know your Greek alphabet, you're like alpha, beta, gamma, but no, that's not what we're going to talk about. We will talk about gamma in a little while, but we're going to talk about the positron next. Now, what is a positron? Well, posit, what does that sound like? Positive. And tron sure sounds like the end of electron. And that's exactly what it is. A positron is a positive electron. Like positive electron. No, electrons are negative. We've been told that our entire chemical lives that electrons are negative. Well, howdy do to you. Turns out you're wrong. Electrons are generally negative, but it turns out electrons can be positive. Have you ever heard the term antimatter? Most people have who are like, science fiction fans because they use that in science fiction all the time. But what is antimatter? Antimatter is the same thing as matter. It's got the exact same properties except the charges are reversed. So protons are negative and electrons are positive. And it turns out, from what I've heard, and maybe some cosmologists would disagree with me, from what I've heard, when the universe first began, when there was the first particle formed, first charged thing formed, there was no particularly good reason for choosing negative electrons and positive protons versus the other way around. And so it was just by chance, 50-50 chance, that one was chosen and the other wasn't. Okay, really kind of cool. So anyway, we've got these negatively charged electrons that we're used to, but it turns out there's these things in the world called positively charged electrons, which are antimatter. Now, these positively charged electrons are going to run around. They're going to find an electron pretty quickly. Those two are going to hit each other, right? That charge attraction is really, really strong. And it turns out they annihilate each other. They emit all sorts of light and energy. But you do make these little positive electrons. Now, what kind of things can undergo a positive electron? Let's do aluminum 24. Now, this is not the stuff that you'd find normally in your aluminum foil. There's going to be essentially none of that in there. So aluminum 24 can undergo a positron. Now, positron, there's two ways people write it. People will write beta plus, but more often they'll write plus 1e. Okay. And so I'm going to use this bottom one, but you will definitely see this, especially textbooks. Textbooks love that one, even though outside of textbooks I don't see it as much. So 0 plus 1e, and then we balance our mass number and atomic number. Mass number didn't change. Atomic number, 13 is equal to 1 plus 12. We run over to our periodic table, and our periodic table tells us that element 12 is magnesium. So we can say aluminum 24 undergoes positron decay in order to form magnesium 24. Now, if you had a hard time imagining where in the nucleus the electrons were in order for beta decay to happen, you're like, okay, I don't really like the fact that neutrons or protons and electrons squish together, but fine. What the positive where are you going to find a positive electron in a nucleus? Well, if you look at a nucleus, there's only one thing in a nucleus that's positively charged, and that's our good friend, the proton. And it turns out a proton isn't just a proton. It's a positron and a neutron squished together. And for whatever reason, one of the protons in there decides, hey, I'm getting rid of my positron. Most things in the universe don't do that, but some do. And so you get this positron ejected. Crazy stuff. So there's actually antimatter inside of you. Every single atom inside of you has antimatter, because every single atom, even the little lowly hydrogen, is made up of protons. Right? There might not be any neutrons in a hydrogen atom. Most hydrogens don't. But crazy. There's antimatter inside of you. All right. Now, if you remember from the last slide, what's a neutron? A neutron, well, that was an electron plus a proton. But what's a proton? A proton is a positron plus a neutron. But what's a neutron? Oh, right? And this is why physicists are so strange. Chemists, we're like, hey, let's just stop there. Okay, proton, positron, neutron, okay. We're done. We're not going to go down that rabbit hole. But the physicists, they like to go down that rabbit hole. It's a crazy little one. Like, when does that end? At what point can you stop breaking these particles down into their little subparticles? I'm not going to go there because I'm a chemist. So we're just going to stop at that first level. All right. So a proton is a positron plus a neutron. That positron flies off. Neat stuff. All right, the next one that we're going to talk about is electron capture. Now, this one sounds a little bit different because you have the word capture there, and that's actually exactly what is happening. So instead of something being emitted from a nucleus, it turns out this nucleus actually sucks in an electron into it. Wow, that's a strange thing. So what can do that? Let's talk about some nickel 59. Nickel is element 28. It can capture an electron. Now, you have to try pretty hard. You generally have to shoot an electron at really, really high energy to get past those other electrons and force yourself into the nucleus there, but it can be done. And so there, because it's a capture process, it's actually happening on the left-hand side. It's adding that to the nickel. And if you add that to the nickel, you get 59 plus 0 is 59, and you get 28 minus 1 is 27, and you actually turn that into cobalt. And it turns out you get a bunch of energy as well. Right? So we release a ton of energy when we do electron capture. So weird thing, not very common. You kind of have to try to make that one happen. It's not happening a whole lot all by itself. So check in just to see how you've been doing. What's the product of beta decay of cesium-137? So beta decay of cesium-137. Go. All right, what did we come up with? Cesium-137, cesium, and we have to go, okay, where's my periodic table? Which one is cesium? And we find cesium down there. He is number 55. And so we go, okay, cesium 55 down there, and that is undergoing beta decay. And you have to remember what beta is, right? It's 0 minus 1b. And then we have to balance that out. 137 equals 0 plus 137. 55 is equal to minus 1 plus 56. And then we run back to our good friend, the periodic table. We say, what's element 56? That is barium. Okay, so we get B, A here. And so 137, 56, barium. And we say, these are all supposed to be 3s. Okay, I corrected that on the play posit for you. So the play posit had the correct numbers there, but my slide didn't. I don't know why I missed that. So cesium-137 turns into barium-137. Okay, so sorry about the mistake in the numbers there. I don't know how those all turned into 5s. It's like they were positrons. All right, a couple more. Proton emission. And you see a little word less common there. It turns out the proton emission only happens in isotopes that we make. People like this. Okay, I've never actually made an isotope myself, but we have these things called these super colliders. You've probably heard of them, where we can throw atoms at each other at really, really high energy and make new atoms. In fact, most of the end of the periodic table is just stuff we've made. It's not stuff we found in nature. Why don't we find it in nature? Because it turns out even when we make them, they have lifespans of femtoseconds or picoseconds, so 10 to the minus 12, 10 to the minus 15 seconds. These things are not at all stable. You're not going to be like doing chemistry with it, right? One element 117, no, there's no 117 chemistry. That thing only exists for such a small period of time. Okay, now, so that's when we see proton emission, is in these things that we make. Now, does that say nature never does it? No, absolutely not. I promise you, in the sun, there's all sorts of nuclear chemistry going on and all sorts of proton emission going on. However, since those things are so short-lived, we don't see them. So we don't really see direct evidence of that. We can probably see indirect evidence of that. You can talk to a nuclear physicist or somebody who studies the sun to ask about that question. So what undergoes proton emission? Let's go ahead and take our favorite element, lutetium, and its lutetium-151 has an atomic number of 71, and it's going to undergo proton emission. We generally represent a proton with just a P, and the fundamental charge on a proton is a +1, and there's 1 proton and no neutrons in a proton, and so 1 plus 0 is 1 for our mass number. And then we balance that out. 151 equals 1 plus 150, 71 equals 1 plus 70. We run over to our periodic table and we find out that's our second favorite element, which is ytterbium. Okay, so lutetium-151 undergoes proton emission to form ytterbium-150. So that literally is just a proton goes out of the nucleus, changing the identity of the nucleus, reducing it by 1. And then the next one, if we have proton emission, we also have neutron emission. This is also less common, right? Only occurring in ones that we've made. And so we get 249 CF, which is good old californium, and you can guess where that was discovered, in Oklahoma. Californium. Okay, California. All right, so californium undergoes neutron emission. We generally represent with an N. It has no charge, which reminds me of one of the best jokes out there. Is neutron walks into a bar, orders a drink. Bartender gives him the drink. Neutron says, how much that be? Bartender says, for you, no charge. All right, now there's 1 neutron and no protons and a neutron, so 1 plus 0 is 1. That's our mass number. And so we do this and we say, hey, look, 249 equals 1 plus 248. 98 equals 0 plus 98. So we still have californium because all we did is eliminate a neutron. That doesn't change the identity of our atom, and so we still have californium. And so californium-249 undergoes neutron emission to form californium-248. Now, we talked about gamma before, And I said, hey, we're going to talk about that later. It's now later. And so what is gamma? Gamma, it turns out, is not a particle. It's just a way of representing some of the energy that comes off of these nuclear reactions. Nuclear reactions actually give off a ton of energy, which is why we have things like nuclear power plants and nuclear weapons. Okay. We'll talk about those later on. But they give off a ton of energy in one way, and because they give off such high energy, is they give them off in gamma rays. And so you're going to see nuclear equations where you've got this stuff over here, you've got your little arrow, you've got this stuff over here, and then you're going to see gamma. And so gamma, again, there's fancy ways of drawing it. I just draw it as a fish swimming down instead of a fish swimming towards the left, which is our alpha particle. And so the gamma particle just says, hey, look, we're emitting a lot of energy in the form of light, and we're going to talk about that as gamma rays. So when you see gamma in there, great, it's good, it's useful, it tells you something, but it doesn't do anything to the balancing. Because, right, there's no protons and no neutrons in gamma, and there's no charge on gamma. And so it doesn't do anything to your balancing. It's just there as kind of informational. Hey, energy came off here. In fact, quite a lot of energy. All right, so let's do some examples. And I'm just going to focus on this portion on the left here. That portion on the right that you saw is just kind of a reminder of what each one does. They're not correlated one-to-one, and that always confuses people. I really should just probably remove that. I would encourage you to pause the video, look at all 4 of these, try to work them out yourself if you want to, but this isn't an interactive question, and so I'm just going to go ahead and do that, but I still encourage you to work on that. So we're trying to find the question mark in each one of these cases, and so we're just going to do our nuclear balancing. 11 equals 11 plus 0, 6 equals 5 plus 1, and so what has a 0 and positive 1? That's going to be my positron. So carbon 11 undergoes positron decay to form boron 11. All right, on the next one, we've got sulfur 35 undergoing beta decay, 0 minus 1. That's beta decay in order to form something. So we get 35 equals 35 plus 0. And we get 16 is equal to something minus 1. That's 17. We go over to periodic table, and we find out that element 17, I believe, is chlorine. Let me double check that. Just my brain is now like, is it really chlorine? Let's go. Yes, element 17 is chlorine, and so we've got that there. Here we're finding the actual starting products. We're saying that something decayed in order to form yttrium-90 and a beta particle. And what was the thing that decayed? Works exactly the same. We have something is equal to 90 plus 0. Well, that's going to be 90. And then we have something is equal to 39 minus 1, and that's going to be 38. And we go and say, oh, look, 90, 38. Let's run over to our periodic table again. We find element number 38. And that is krypton. And so we say that is that right? Oh no, I'm like, that's not right. I couldn't read my own periodic table. Element 38 is strontium. I'm like, that totally doesn't sound right. Strontium. Okay, so strontium-90 undergoes beta decay in order to form yttrium-90. And our last one here, this one's a little more standard. We've got 210 equal to something plus 4, and that's going to be 206. And we've got 83 equals something plus 2, and that's going to be 81. We run over to our periodic table, and we find element number 81. Where's element number 81? We had bismuth before, and 81 is going to be thallium. There we go. So bismuth 210 undergoes alpha decay in order to form thallium 206. All right, so is that it? Something undergoes nuclear radioactive decay and it's done, it's no longer radioactive? And the answer is no. Most things that are radioactive actually turn into other radioactive things, and you get what's called a decay series. This is more informational than anything else. I'm probably not going to test you on decay series quite specifically, but I just want you to realize that it's not just like one and done. So if we take uranium-238 up there, it turns out what it's mainly going to do is it's mainly going to undergo alpha decay, and then it forms thorium-234. But that thorium-234 is also radioactive and generally undergoes beta decay. And that beta decay forms Pa-234, and then it does it again and forms uranium-234 again. Interesting. Notice we just formed uranium again. Okay, we just lost now 4 of our neutrons. And then those undergo alpha, 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 and we get down here to polonium-218. It turns out then it bifurcates, and we can actually have two different decay processes, and both of which happen just at slightly different rates. One happens more than the other. I don't happen to remember off the top of my head which one happens more than the other. But you get alpha, then beta, you get beta, then alpha, and then it turns out you end up at the same spot, which is bismuth. And then you do it again. You turn out you get lead. And then you get bismuth again. And then you do it again. And eventually down here you get to lead-206. And lead-206 is a stable isotope. And so you find that there is a bunch of lead. And we're actually going to use this particular decay process later, that there's this ratio between uranium-238 and lead-206 that tells us something about how old something is and how long it's been decaying. Okay, so just be aware that most nuclear decay processes, especially for very, very large atoms, are not one and done. There's several steps to it. All right, we're going to talk about a couple periodic trends. What do we see on the periodic table? So we're going to start with H, and we're just going to look at the number of protons and the number of neutrons in the most stable isotope. We're going to do that by looking at the atomic mass on the periodic table. While hydrogen has one proton, and its most stable isotope has a mass of about 1, right? 1.007925 is the atomic mass of hydrogen. And so how many neutrons is that? Well, it's 0, because neutrons, if you remember, both weigh 1 AMU. Protons and neutrons both weigh 1 AMU. So if there was 1 proton and 1 neutron, it would weigh 2 AMUs. Since our average mass is closer to 1, that means on average we have more things with 1 protons and no neutrons. Helium, we know, has 2 protons. And if you look at the periodic table, it's got an average atomic mass of 4. So 2 plus something is 4. That's 2. So the most stable isotopes of helium generally have 2 neutrons. So 2 protons, 2 neutrons. Then we go to lithium, and we're not going to do the whole periodic table, don't worry. It's got 3 protons, and if you look at its average atomic mass, it's about 7. And so 3 plus something is 7. And so we get the most stable isotopes of lithium have about 4 neutrons. Let's jump just a couple into boron. And boron has 5 protons. It has an average atomic mass of 11, and so you get 5 and 6. We're going to do one more, jump all the way down to calcium. 20 protons, average atomic mass of 40, so it has about 20 neutrons. So what I wanted to show you in this table, and we could do a bunch more, is that at least for the small atoms, what we're finding is that the number of protons and the number of neutrons are either equal or they are roughly equal, with the number of neutrons maybe being slightly higher than the number of protons. And those are going to be our most stable isotopes. Why do I say those are our most stable? Well, because more of them are forming in the universe than these other isotopes. And so that must be the most stable one. When we look at those average atomic masses, we're saying, hey, this guy is more stable because it's forming more often. And so there's got to be this trend that says there's a ratio of neutrons to protons that's actually the most favorable. And that ratio is about 1 or maybe slightly higher than 1. And it turns out that's true. And when we get too far off of that ratio, when we get too far higher than 1, we're going to undergo nuclear radioactive decay to try to get towards that ratio. And if we're too far above, did I say above or below? I think I said below. If we're now too far way above that ratio, we're going to undergo nuclear radioactive decay in order to get to that ratio. So there is this kind of stable ratio that is part of the reason for nuclear radioactive decay, is if you have too many neutrons or if you don't have enough neutrons, you're not stable. Okay, so that's what we call the valley of stability, is roughly that ratio of 1.25 is kind of the number that people generally use. 1.25 is the ratio of protons to neutrons for kind of some of the heavier elements out here. For some of the very light elements down here, it's kind of more 1-to-1. You see there's that red line there drawn. What they're showing in these ones is the number of neutrons on the y-axis, the number of protons on the z-axis, right? That's essentially the identity of the molecule, and then you count the number of neutrons. And there's 2 different charts. This one on the left comes from the Wikipedia, I saw it there, and this one on the right comes from the TRO textbook. And you can see very clearly that on the one from the TRO textbook, there's these little green dots, and the green dots are the most stable isotopes. And so those green dots kind of go on. You can see that there's a ratio of 1 at the beginning, 1.25 in the middle, maybe 1.5 at the end. But 1.25 is kind of a rough guide that people use. And what do we see? That if we are right on that ratio, we have green dots and we have stable isotopes. But if we go above that or below that, we no longer have stable isotopes. And in fact, this chart on the left does a really good job of showing what happens when we no longer have stable isotopes. So let's look up here in this blue region. So let's look at, say, elephant. I just said elephant. Element number 50, okay? So let's find 50 on our periodic table. What is element 50? So that's tin, okay? So we've got 50, tin, and what are we going to do with that? We're going to find that if we don't have enough neutrons, so tin would like to have a ratio of about 1.25, so about 75 neutrons. And so what we're going to do is we're going to go up here. If we don't have enough neutrons, so we're down here at 50, it would rather have somewhere around 75. If we're down here at 50, then we're going to have a mass number of 100, right? 50 plus 50 is 100. But this one's not going to be stable, because what it really wants is to be somewhere more around here, which is in the roughly 70-ish range or so. That would be a mass number of 120. So what's this going to do? It's going to undergo a nuclear radioactive decay process that will get it towards that goal. Okay? So what's going to get it towards that goal? What's going to get it towards that goal? Well, it's got to increase the number of neutrons. How's it going to increase the number of neutrons? Well, it turns out by far the most common path of increasing the number of neutrons is what's in orange here, which is beta plus decay. And if you remember, beta plus is positron, and so that's turning a proton into a neutron, right? What does that do? That increases my number of neutrons and actually decreases my number of protons. And so you'll find that a lot of things, huge numbers of things that are below the valley of stability, by default undergo beta positive or positron decay, because that's a way of increasing the number of neutrons as we go along, getting us closer to that valley of stability. Doing that, since it changes a couple things at once, I'm sorry, it doesn't. It actually takes us this direction, right? No. Yeah, it changes this direction. It reduces, I had to think about it. It reduces our atomic number and increases our number of neutrons. So it takes us kind of in the top, upper left direction. So we're getting towards that valley of stability, which is what we want. All right, so what happens if we have too many protons? So let's say we wanted in the 70s, but now we've got up here 82, 50 plus 82. What's 5 plus 8 is 13. That's going to be 132. And so we have too many neutrons. Well, what is the thing we're going to do? We're going to try to get rid of neutrons. How do we get rid of neutrons? Let's turn them into protons. So you'll see that blue up here, the most common thing is beta minus. That's beta decay, which says you release an electron and you turn a neutron into a proton. And so there we are decreasing the number of neutrons because we're turning a neutron into a proton, and that is our primary decay process. Now, that's the main two that happen at these lower numbers. You'll see some proton emission down here and things like that, but that's the main things that are happening is beta plus, positron, and beta minus, which is just beta, electron decay. But as you get up here towards the bigger ones, you start to see some other things, which is alpha emission. Now, alpha emission, right, is just 4,2 helium, if you remember. And so you're emitting 2 protons and 2 neutrons at the same time. You'll notice that these alphas tend to occur below the valley of stability. So what does that mean? We have not enough neutrons, right? So that's not enough neutrons. Right? If we don't have enough neutrons, how does emitting 2 protons and 2 neutrons get us more neutrons? And it doesn't, but it gets us a better ratio of them. And you can kind of figure that out as you do it. But that's essentially what happens. I'm not going to go over the math of it, but you can actually figure out that as you emit those things, because we generally have more neutrons than protons. As you emit 2 protons and 2 neutrons, you're actually getting closer to a ratio that has the right number of protons and neutrons. But you can remember, if you want, that below the valley of stability, alpha decay for the heavy ones, positron decay for the lighter ones. Okay. On a test, I'm going to give you this chart on the right. So you're going to see this chart on the right with the valley of stability there. And you're just going to have to know that down here versus up here, what are you going to find as your different modes of decay? You're not going to get this beautiful one over here that kind of has all that for you. All right. You don't need to know anything on this chart, but it's an interesting chart, so I'm going to talk about it. This just says the number of stable isotopes that exist for each element on the periodic table. You can see a bunch of red there, which means that there's no stable isotopes. The actinide series, there's not a single stable non-radioactive isotope of any actinide on the periodic table. This whole bottom row down here, all these elements, especially those new ones, they're right there, the 112s, 111s to 118s, right? All of those have no stable isotopes that exist. They're all radioactive, in some cases very, very highly radioactive, and very, very short-lived. Okay? But as we go into other parts of the periodic table, you can see some blue. I mean, xenon, tin, mercury, lead, those things have a bunch, right? 6, 7 different stable isotopes that exist. But what we're going to look for is we're going to look for some trends on here. And it's not always immediately obvious to people, but I want you to look in the columns and the groups on the periodic table and see if you see any trends. It's especially evident in the transition metals. So if we look at the groups on our transition metals, what do we notice? That every other column is kind of orange and red. And if every other column is kind of orange and red, what is that saying? It's saying that I've got either 0 or 1 stable isotope. But in between those oranges and reds, there's a bunch of blues. And what are my blues telling me? 4, 5, 6, 7 stable isotopes. So what's going on here? Well, if you look, the difference between the orange ones and the bluish ones are these guys have an odd number of protons, and these guys have an even number of protons. And it turns out that nature loves things in pairs. Right? Electrons come in pairs, but it turns out protons come in pairs, and there's a stability to having those pairs filled. So even numbers are lucky numbers. If you totally just count up all of the stable isotopes on the periodic table, the number with an even number of protons and an even number of neutrons, there's 157 of them. But if you take even and odd, there's only 53, or odd and even, there's only 50. And even if you add those up, there's only 113 odd and evens versus 157 even and evens. But here's the one that's really the kicker. The number of stable isotopes on the periodic table that have an odd number of protons and an odd number of neutrons is only 5. That's amazing. It's such a favoring of even numbers. So nature loves even numbers, even in the nucleus. And it turns out that's because nucleus, the protons, they're quantized. They have these levels that they can exist in, and they exist in pairs. Neutrons, quantized. Just like we talked about electron levels like this, and we said, oh, look, we can draw pairs of electrons. It turns out that in the nucleus, the protons and the neutrons are also quantized, and they exist in these pair levels. And the pairing imparts energetic stability. So even and even is by far the most common thing you're going to see on the periodic table. So if someone asks you, oh, I've got an element like nitrogen, and it's got 7 protons, and I'm going to say I've got nitrogen 14, your likelihood of that being stable is actually pretty small because it's odd and odd. Now it turns out nitrogen 14 is stable, but your odds of it are pretty small because it's odd and odd. So neat stuff. So we learned something about nuclear radioactive decay. We learned the different modes of nuclear radioactive decay. We talked a little bit about how to balance nuclear reactions. We talked about the stability of these things, why they're going to undergo decay processes, how to predict it based on where it lies relative to the value of stability, and then a little bit about these odd and even numbers. Again, you don't need to know anything about the odd and even numbers. That was just a cool chemistry fact. Thanks so much for listening, and have a wonderful day.